Everyone, I'm Ricardo Rodríguez from the University of Zaragoza, Spain, and I'm going to present a work on challenges in verifying trusted executable finds in memory forensics. So, I guess you already know that a common incident in the security in systems is the presence of malicious software, malware. As a way of making the security incident response process in the system, we have two different kind of forensic analysis. So we have computer forensics and network forensics. Computer forensics are focused on disk forensics and memory forensics. In the case of memory forensics, the analysis of the data is performed on the memory of the system. While in the case of disk forensics is more related to the device drivers. Network forensics, on the contrary, is more focused on the analysis of the network traffic. So it is important to analyze the memory because sometimes the access to physical device drivers are difficult to achieve. Moreover, we have less capacity in the case of memory than in the case of disk. So if we have less data, this will make easier for us to make the initial triage. Moreover, some of data may only reside into memory. The file that contains the memory dumped from a system to a file is named memory dump. And this file is going to contain a lot of data which is valid to analyze. Each one of these elements are named memory artifact. We can find here the snapshot of the running processes, logged users, open files, or either open network connections. Or we can also have some resources that has been freed recently on the system. Since normally the operating system is not going to zero out these memory zones, we may find this content still available on the memory. Of course, we can have here some problems already because we can have memory inconsistencies if the memory is acquired in live systems. Since the memory, the process of memory acquisition takes some time, it may happen that we can have some changes in the memory during the acquisition. In order to assess the reliability of the analysis results dealing with this, recently Pagani et al. Has proposed the incorporation of temporal dimension in memory forensics. So regarding code signing is a way to establish trust in computer software, and it's commonly used in modern operating systems such as Windows. So if you download a program binary from the internet and is not signed, Windows UAC is going to ask you for permission. Code signing is a way to authenticate from where the software comes from, as well as to guarantee the code integrity. Recently, some malware developers are trying to incorporate code signing into their programs in order to deceive users to execute them. Fortunately, at the moment, this is not very common, and this is happening because either the certificates has been compromised or the certificates has been used directly to malware developers. In this way, certification authorities are in charge of making revocation process of any abuse certificate. So the idea here is, well, can we use code signing as a preliminary step in order to prioritize the list of suspicious processes in a memory dump for further analysis? However, we have some problems that are going to to make this a little bit difficult. First, we have the inaccuracy of process and program application. Then we have memory swapping, and then we have relocation. I will go on these details after. So, in this paper, we research to what extent these issues can affect negatively the signature computation. And also we try to see if there are some other issue of relevance that can affect to this computation, as well as the possible solutions. Well, we rely on here we are researching on Windows. In this case, we has focused on signed Windows files. They follow the Microsoft Authenticode standard, which is the code signing standard used by Windows. Okay, it follows the PKCS 7 structure. So we are going to have a signature and a timestamp, which is optional, and a certificate chain. In the case of the certificate chain, is built using the X509 chain building rules. So a signature in a Windows file can come in two ways, either embedded or catalog based. In the case of embedded, we are going to find a structure of the portable executable header in which we have the signature. In the case of catalog based, the signature is in an external file, which is a catalog file. This is a collection of digital signatures, and furthermore, these files are signed in order to prevent unauthorized modifications. The verification of a signature in the case of Windows can be performed through Windows functions, mainly found on these two DLLs. If you want more details about it, you can read on the paper. So we rely mainly on these structures, file objects. A file object is going to be a structure with it's a kernel level structure that is used to link the file data stored in the physical disk with the data used by the kernel and user mode processes. This structure maintains a pointer to another structure, which is the secure object pointers, in which we have three opaque pointers, and we are interested here in this both of here. Okay, the thing is that data section object is going to be used to track the state information of a data file. So, for instance, every time that you open a file on Microsoft Word, this object is created on the kernel side. In the case of executable files, a data section object is going to contain the executable file as already contained in the device. Also, it may contain some encoding. In the case of the image section object, this contains the image file. This means after the relocation has been done, and it may also contain some encoding, and the authentic or signature data is stripped. So we found that the section that contains the signature it is not there. This it may happen because the Windows payloader knows that has already checked the signature, so it not needs this anymore. However, we found that the relocation section still remains, which is a little bit curious. Well, we have developed our plugin, which is named SigCheck, as the tool of Microsoft in order to verify signature. Our plugin verifies digital signatures of executable files in memory dumps. It works for X, DLL, and sys files, and is a plugin for volatility 2.6. It has some dependencies, as you see here, and it has been released under GPL versions releases, so you can check out on the website. If you want more information about how it works, you can check it in the paper. You have the pseudo algorithm there. So let me tell you that we have different outputs, so you can have different returns depending on if we are able or not to verify the signature of the file. In the case of the verification, we rely on OpenSSL, and then we return the typical return results regarding the verification of certificates. As a side product, we have Sig Validator, which is a Python script to verify the PE files as in disk, so similar to the Windows SigCheck tool. So we have performed two kind of experiments. First one is to check the effectiveness of our tool. So we have deployed Windows 7 SP1 in a virtual machine in both 32 and 64-bit architectures, and we have also installed some common workstation software. We have executed every virtual machine 10 times in and captured the memory in 4 different time moments, at the first boot and after 10, 20, and 30 minutes of user activity. As user activity, we have considered data documents open and some watching on the YouTube. So these are the graphs, the plots of the results. So regarding the discussion, we found that there are more chances of retrieving file objects with complete data at first boot. 32-bit scenarios provide better results than 64-bit, and almost half of the 32-bit driver files are successfully verified as catalog sync files, and this percentage drops to 30% in the case of executable and DLL files. We found that many file objects are partly retrieved, and that none of the file objects retrieved in any scenario contain the authentical signature as embedded signature. We have also performed some analysis using some experiments using signed malware. We have selected some samples. You have the information about these samples on the paper also, and also the certificate issues. I mean the problems with this signed malware. We have checked 3 different tools: the Windows UAC, sysinternal SIGCheck, and also the side product of our plugin, SIG-Validator. Okay. So we found that the Windows UAC and the SIGCheck are more focused on the publisher trustfulness. Unlike our plugin, a certificate expiry is not reported to the user. We also found that the messages shown to the by the Windows UAC to the users are less intuitive, and self-signed certificate is detected by the 3 tools, but the text messages differ slightly. Most interesting result is malware 04, which has a revoked certificate. In this case, sysinternal SIGCheck warns about it, while the Windows UAC tells the user that the file comes from a verified publisher. This may be caused because the parameter settings when calling to the Windows function to verify the signature. In the case of our plugin, it returns a successful verification, since we rely on OpenSSL, and OpenSSL currently does not support the certificate revoking checking. Well, regarding the limitations, we have data incompleteness, because in the way that the Windows memory system works, it may affect the computation of the authentical signature. Remember that authentical signature is going to compute a hash, and in this case, just a single flipped bit will change totally the hash. So we have memory swapping, page smearing, and demand paging. Solutions here may be to guarantee that the Windows payload other logs memory pages that contain file objects, or either to use a combined analysis of a memory dump and their corresponding swap files. We have also another limitation, which is the PE relocation. Okay, so these are the changes on the image-based address due to the relocation. So here the solution could be to have a database storing the version information, authenticate hash, and image address value for every system file. Of course, this could be infeasible in practice given the huge number of these files. In the case of the catalog signet files, many of the system files are signed by catalog. This means that we need some kind of database to maintain this information. Last but not least, we have inconsistencies between the executable file and the process. This is one of the biggest challenges in memory forensics, is how to guarantee that the binary code of an image file was unmodified, right? Because the mapped file, I mean the file in this, can be legit, but the corresponding process can be malicious. So if we have code injection or process hollowing attacks, these are going to be undetected, because we rely on the initial structures that we have on disk. So this is also undetected by common forensic programs such as Process Explorer, Process Hacker. Here we can use other plugins to detect malicious code or similar digest comparison. So There are some people that has already studied the presence of authentic code signet files in malware landscape, and also the weaknesses of code signing in Windows. All of the works are focused on executable files rather than image files, as we do here. Furthermore, as far as we know, we are the first to formally document the limitations and the solutions that memory forensics impose to the analysis of authentic code signet files. So moving to conclusions, Windows PE loader and Windows Memory Subsystem affect to the forensic memory forensic analysis due to the relocation, paging memory, pages mirroring, and demand paging. So, in summary, the verification of digital signature of process capturing in a memory dump becomes a difficult task. Okay. As limitations, we have data incompleteness, data chains caused by relocation, catalogs in files, and executable file and process inconsistencies. So we have developed a plugin for volatility that enables an analyst to verify a digitally signed file, if feasible, retrieved from a memory dump. It relies on internal operating system structures, in particular the file objects that we have commented previously. So let me conclude saying that the success rate is low, especially when the memory is acquired from a system that was running for a long time. Thank you for your patience and your attention. If you have any questions, I will be glad to answer it.